And we're back really now to wrap up 17-3. We did run out of time as we're going through that advanced problem where we took ice at -5 degrees Celsius and brought it all the way to steam at 115 degrees Celsius. And so now we are going to wrap up this chapter by talking about the heat of solution. And so you have another value, just like you have heats of fusion, heats of vaporization, heats of solidification and condensation, etc. You also have the heat of solution, which is given the symbol delta H SOLN. All right, which is just simply going to be the amount of heat released or absorbed when a substance dissolves. All right. And so, for example, if you take sodium hydroxide and you dissolve it in water, it's actually quite exothermic. It heats up quite a bit. And so the delta H of solution is a negative 445.1 kilojoules per mole. It's quite a bit. Sulfuric acid has a very, very high delta H of solution. As you add water to that, in fact, it can boil the water. When you dilute concentrated sulfuric acid, you have to do it in an ice bath to keep the temperature down. Otherwise, you'd be boiling the water and splattering the acid out of the container. You don't want that to happen either. All right, so just simply dissolving something in water is going to either release or absorb energy. Now, there are practical applications for this. For example, when you want to make something hot, so say as a hot pack, this is common in the wintertime, what they do is they put a wafer that contains calcium chloride in it. You break the wafer, and it's going to dissolve in the water. When it does that, it releases energy. The delta H of solution, or the heat of solution, for calcium chloride is a negative 82.8 kilojoules per mole. And that's what actually heats up that hot pack. This is also, by the way, so if you want to, we can just call this is the hot pack. It is also under the name of driveway heat. In the wintertime, when you have snow and ice on your driveway, ice after you've shoveled it, you can put calcium chloride down, and the fact that it's a salt is going to lower the vapor pressure and it's going to allow the ice to melt. But the added aspect of this is that it heats up as it dissolves in that melted ice. And so that added heat helps to melt the ice even quicker. So that's why it's called driveway heat, as opposed to just taking rock salt, which you throw down, which is typically sodium chloride, and you don't get a whole lot of energy change there. So the effect really is just from the lowering of the vapor pressure. But anyway, so calcium chloride has a couple of different applications in terms of its heat. It also is used as a desiccant in desiccators. Anyway, that's a whole different story. Now, you can also have the opposite effect. For example, in a lot of medical kits, you have cold packs. And in a cold pack, you take ammonium nitrate and you dissolve that into water. When you do, it actually absorbs energy. So the heat of solution in this case is going to be a positive 25.7 kilojoules per mole. That's going to feel cold to the touch, and so if you twist an ankle or something to that effect, you can crack the wafer in the cold pack, which is going to be your ammonium nitrate, shake it up so that it dissolves completely, and voila, you have something that's very cold, at least for a short amount of time. So there's definitely some practical applications to this. But let's go ahead and try a problem, which is going to be the exact same type of problem as all of the other changes of state. How much heat in kilojoules is released when 2.5 moles of sodium hydroxide is dissolved in water? So we take our 2.500 moles of sodium hydroxide. We're already in moles, so we're good so far. Go ahead and revisit. It's a negative 445 kilojoules per mole. Of course, you don't need the negative sign. If we say that it's released, we know it's going to be a negative delta H. So this is just times 445.1 kilojoules per mole of NaOH. Notice it is only 1 mole of NaOH. Those divide out, and you can take your 2.5 times 2.5 times your 445.1, and you get 1100. We'll just call it 1113 kilojoules of heat is released. So that's going to be quite hot. All right. So in summary, you're going to have to calculate changes in energy when substances change state or get dissolved. Sometimes they absorb, which have a positive delta H. Sometimes they get released, which means that they have a negative delta H. Just watch for your units. Make sure that they all cancel out properly, and if you do that, you shouldn't have any problem getting to the final answer. Okay? That really does now conclude 17.3.